Hi, I am 3 honor students. It's Miss Mack, and we are going to do section 7.6 properties of radicals today. And bear with me, we've got a lot to talk about. So let's get started. 7.6 properties of radicals. Okay, we are going to talk about 5 properties today. The first property is when you have the nth root of a times b. You are allowed to break that up into the nth root of a times the nth root of b. The reverse is also true. If you have the nth root of a times the nth root of b, you can combine them into one nth root. The only condition is that the indexes are the same and it's multiplication. If you have division, if you have the nth root of a over b, you can also break that up to be the nth root of a over the nth root of b. And if you have a broken up radical and they both have the same index, you can put them together if it makes your life easier. Those are our first 2 properties today. So make sure you have them written down correctly. Our third property today is if you have the nth root of b to the m. So here we're taking an nth root of b to the m. And here you would probably take your b and raise it to the m first and then take the nth root. But you are allowed, if you prefer, to make your number smaller, take the nth root of b first and then raise it to the m power. Okay? So you have a choice on which one you do first. All right, our fourth property. If you have an index that can be factored, we'll make it km or k times m. So like 6 could be changed to 2 times 3. So if you have an index that can be factored, you are allowed to break that up into 2 radicals. So here you would have the k root of the mth root of b, or if you prefer, you could do the mth root of the k root of b. So you can do it either way. So if you have a large index, you can break it into a smaller index by factoring it. All right, our 5th property is the most neglected property out there. Students always forget this one. And it's because we don't teach it this way until higher level mathematics. So here we go. The nth root of b to the n, you have always, that's an n, you have always known is b. Okay? You have known that as b. However, that is only true if our index is odd. If our index is even, what happens is we actually need absolute value bars around that b. It's actually the absolute value of b because it's forced to be positive. So in order to take a square root, that value in there needs to be positive in order to do a 4th root, a 6th root, etc. So this has to be the absolute value of b. When it's odd, you can have a negative, but when it's even, you can't. So it has to be the absolute value of b. So when is it that we use this? Well, we use this when our index is even, our exponent is even, and our final answer has an exponent that is odd. So we call this even, even, odd. And when we have an even, odd, then we need opposite dominant. And I'll show you, oops, let me move that over. I'll show you some examples of that in a minute. So those are our 5 properties today. Okay, example number 1. We're going to do quite a few bits for example number 1. So we're going to simplify. And for part A, we're going to simplify the square root of 98. So when it's a square root, you need to be thinking in terms of perfect squares. So what is a perfect square inside of 98? Perfect square inside of 98 is 49. So we are going to break this up into be the square root of 49 times the square root of 2, just like our property up above said we're allowed to do. And the square root of 49 is 7, so my answer is 7 root 2. Let's go on to B. B says that we have 3 square root of 75. So we're still thinking in terms of perfect squares. And so what perfect square goes into 75? So this is 3 times the square root of, the perfect square inside there is 25. And 25 times 3 is 75, so the square root of 3. And then the square root of 25 is 5. 5 times 3 is 15 root 3. So that is our answer. All right. Let's go on to C. And for C, I'm going to do the cube root of 72. The cube root of 72. So now I'm not thinking in terms of perfect squares anymore. I'm thinking in terms of cubes. And so 2 cubed would be 2 times 2, 2 times 2 times 2, which would be 8. And 3 cubed would be 3 times 3 times 3, which is 27. And 4 cubed would be 4 times 4 times 4, which is 64. So these are perfect cubes. And so which one of those perfect cubes goes into 72? And the answer is 8. So we can change this to the cube root of 8 times the cube root of 8 times 9 is 72. And the cube root of 8 is 2. And so my answer is 2 cube root of 9. Now 9 is a perfect square, but this isn't an index of 2. This is an index of 3. So we cannot simplify that any further, and that is our answer. All right, we're going to do one more. We're going to do D. See if I can squeeze it on this page here before I go on to the next page. D. All right. And D is going to be 2 the 5th root of negative 96. So this time, I need to think about powers of 5. Now that's kind of weird. 2 to the 5th is 2 times 2 times 2 times 2 times 2, 5 times. So 2 to the 5th is, if you don't know, 32. And 3 to the 5th is big. Let's see what 3 to the 5th is. 3 to the 5th is 243. So 243 is way too big to go into 96. So it must be 32. So we're going to break this up. And it is an odd index here, and I'm dealing with that negative. So I'm going to change this to be 2 5th root of negative 32 fifth root of 32 goes into 96, I think, 3 times. Okay? So, just in case you were worried about that negative, we can take the fifth root. That's down here. Oops, let me clear that out. 5, math. The fifth root of negative 32 is negative 2. So this is going to be 2 times negative 2, which is negative 4, fifth root of 3. And that's going to be your answer. Now these are going to take practice. Sometimes they might be a little difficult. Do the best you can, work through it. If you have questions, make sure you ask. All right, we're going to go on to example 2. If you're a little overwhelmed, pause the video and come back to it when you're ready. So example 2, simplify. Okay, and this time A is the fourth root of x to the 8th. All right. Now what our property says is that you can break this up essentially, right? So you could break this up to be the fourth root of x to the 4th times the fourth root of x to the 4th. And that will give you x times x is x squared. But there's a much easier way to do the problem than that. And that is, if you ask yourself, how many times does 4 go into 8? So you take your index and divide it into that exponent. And so it goes in twice. And it goes in nicely without any remainders, so your answer is just x squared. 4 goes into 8 twice, so your answer is x squared. So that's kind of a shortcut. Here's the long way, and this is the shortcut. All right, let's try B. For B, we have the cube root of x to the 4th, y to the 6th. Okay, I am going to use the shortcut method here as opposed to breaking it up. Now, I could break it up if you wanted, but you should get used to doing it this way. Okay, so I'm going to ask how many times, and I do this part typically in my head, how many times does 3 go into 4? 3 goes into 4 once with 1 left over. So I'm going to have one of my x's on the outside and one of my x's left over on the inside. This is on the outside and this is on the inside. Now I'm going to deal with my y. 3 goes into 6 twice, no remainders. So I'm not going to have any y's on the inside, just on the outside. So it's going to be y squared. And that is my answer. All right, let's try another one like that. So then C is the square root of a to the 6th, b to the 5th. Now when there's no index written, your index is 2. So here, how many times does 2 go into 6? It goes in 3 times. So I'm going to have a to the 3rd. However, this is even, and this is odd. So I'm actually going to have the absolute value. I typically only put the absolute value on the a, but you could put it on the a cubed as well. And then how many times does 2 go into 5? It goes in twice with 1 left over inside the square root. And that is your answer. It's a little complicated, so take your time. All right. I'm going to go ahead and stop the video, and that'll be part 1. And then part 2 will be doing more adding and subtracting and different things with radicals. So that's the end of part 1, but don't